go.
So now we start chapter 5, Dynamics and Newton's Laws. So we use the equation F equals sum of the forces equals to mass times acceleration. So this chapter, pretty much this is the main law that we have to work with. Newton's law, the sum of the forces on an object is equal to mass times its acceleration. Then we'll introduce friction. Kinetic friction is equal to the kinetic coefficient of friction times the normal force. And then the static friction force is greater or the same as 0, less or the same as mu Sn. So that is called the coefficient of kinetic friction. Kinetic friction, and then this is coefficient of static friction. So then we'll introduce friction force into problems that requires us to analyze the friction force between a block and a surface, and then solve the acceleration of the system. So let's review a little bit about units. Kind of a review of what we did the first day. We have mass, which is we're going to deal with a mass a lot, and then we have weight, and we have force. If you remember the first day, we mentioned that in the SI unit system, the metric unit system, mass is measured in kilograms, weight is measured in newtons, and force is also measured in newtons. Right? So essentially, weight is a measure of the force of gravity on your body. And then in the British system, mass is measured in slugs, and weight is pounds, and force is also pounds. So the conversion from there is 1 kilogram is 9.8 newtons. So with this conversion, you can convert from here to here, right? So if you have a mass of 1 kilogram, you weigh 9.8 newtons on Earth. And then if you have a mass of 1 slug, you weigh 32 pounds. So with that one, you can convert from here to here. So both of these have to do with the acceleration of gravity on the Earth, which is 9.8 meters per second squared, and 32 feet per second squared, right? And then the other conversion is 1 kilogram is equivalent to 2.2 pounds. And then with that, you can convert from here to here. So most often, problems will be given to you either in pounds or in kilograms. And then once if it's given in pounds, usually you don't have to necessarily convert to the metric. You can stay in the British system. Okay, so let's start with an example where it's a vertical motion. We'll make it a 192-pound person gets in an elevator and accelerates up at 8 feet per second squared. And then goes up at constant speed for a while. So 192-pound person gets in an elevator and accelerates up at 8 feet per second squared. So let's say the elevator is on the ground floor, and then you're accelerating up at 8 feet per second squared, right, for a little bit. And then after that, you go at constant speed, constant velocity or speed, and you go like that, and then at the end you're gonna slow down, right? So then your acceleration is down. So you're gonna keep going. You're gonna keep going up, but you're gonna slow down until you come to a stop. And then over here, you stop. So then we can ask, what is their apparent weight of the person in each of these three stages? In the acceleration stage, in the constant speed stage, and in the slowing down stage. So what is the apparent weight of the person in each stage? So when it's asking apparent weight, what is it asking? What is it asking for? How do we solve that? One way to answer that is if you put a scale below him, right? What will the scale read? That's thinking. That's
weight to the elevator.
yeah.
Versus the speed of his own weight possible minus the
Acceleration. Okay, something like that. Yeah, his weight, his regular weight plus or minus the effect of acceleration, right? So so basically, if you're sitting on a scale, what would the scale read? Well, there's a normal force that the scale is pushing up on you, right? The ground pushing up on you, supporting you. But if you're accelerating up, the normal force has to be larger than your regular weight, right? So this is N, and then NG. Notice I drew the N larger than your weight, because in the first stage, you're accelerating up, so you're. In other words, if something is accelerating up, there must be a net force that is up on the object. So your weight will always be down. So if you're accelerating up, the ground has to be pushing you up with a force greater than your regular weight. So N minus mg is equal to ma. So when we ask for apparent weight, we're asking for the normal force. That's your apparent weight. Okay, so then let's see here. What's the mg? Well, in this case, the problem is given to you in British system. The 192 pounds, is that the mass of the guy or the weight of the guy? Right? Remember, pounds is the unit of weight or force. So that means that's the weight of the guy already. So that's the mg essentially, is the 192. So now we have to calculate the m of the guy. And that's going to be in slugs, right? So how do we calculate m? Well, if you're 192 pounds, the conversion is 32 pounds is 1 slug. So that's going to be the m. Convert your weight to slugs. So that's going to be 6 slugs, right? So 6 is your mass, and your A is A. So now 6 times A, and then what's the A in this case? 8. So 6 times 8 is 48, plus 192. What is that? 240 pounds. That's amazing, right? For a couple seconds, how long it takes the elevator to accelerate up, you're feeling a force that's pushing you up greater than your weight. And so you actually feel 240, and the scale will read 240. Scale reads 240. it's interesting to kind of think about this question. What if the same elevator was in outer space, where if there's no gravity, let's say the elevator's in the middle of nowhere, and the elevator was accelerating up with a acceleration of 8, right? In outer space. Then what would the apparent weight of the person be? So now you have just N, you don't have mg, right? So then you just have N is equal to ma. So then you have 6 slugs times 8. So the person feels 48 pounds. If you're in an elevator and the elevator is accelerating up, the person will think that he's 48 pounds. So he will almost think as if he's on a planet, riding on a planet, and he weighs 48 pounds, right? How about if the elevator was accelerating up in outer space? How about if the elevator was accelerating up with an acceleration of 32 feet per second squared? I should put here feet per second squared for the units. How about if the acceleration was 32 feet per second squared? What would he weigh? What would the scale show? Well, then it's just 6 times 32, which is 192. Right? So that means if I hit you over the head and you go unconscious, put you in an elevator, take you out to outer space, and have the elevator accelerate up at 32, you would have no way of knowing that you are on Earth or in outer space, because you still feel the regular weight, right?
So like in sci-fi movies, I kind of see like spaceships where they kind of rotate.
Yes, you can
And
simulate gravity.
You could simulate gravity.
Yeah,
That's why
this is a simulated gravity, basically.
Yeah. Okay.
You're in outer space, and you're accelerating up at 32 feet per second squared, and you're 192 pounds, so you're just like, you don't feel any effect. If I close the windows, you feel like you're home, right? Whose theory is this that we have just discovered by just thought process? His name starts with the letter E, and then I, and then N. Huh? This is Einstein's theory of general relativity, right? His theory of general relativity states that the effects of accelerating reference frame is the same thing as the effects of a gravitational field. So you can simulate gravity by just putting you in an accelerating reference frame. A circular motion is one reference frame that's accelerating, right? If I put you on a circulating thing, I can simulate gravity that way. If I put you in an elevator that's accelerating up, I can simulate gravity. So you can almost think of a journey. This is Earth. I put you in an elevator and have the elevator accelerate at 32 feet per second squared, and then have it go to our nearest star, Proxima Centauri, I think Alpha Centauri. There is an Earth-like planet there we discovered about a couple of years ago around our nearest bright star, Alpha Centauri. It's 4.4 light years away, the star. And then there's another planet that looks like ours, sister planet. So that's 4.40 light years away. So if I could put a bunch of people there and start a new colony, how long would it take for you to get there? No, you're accelerating at 32 feet per second squared.
Wow.
Why? Because I'm trying to make you think as if you're on Earth. Because if I put you in a spacecraft and just whiz you at the speed of light, you might not be trained for that. But this way, regular people can even get there. But I can even put babies there. I can have a big satellite with hundreds and hundreds of people with different things.
But that's acceleration, right? Not the speed.
The initial velocity would be 0.
Right.
And then just shoot you up with I probably have to give you some velocity to escape the
Oh, okay, I see what you're saying. So
Yeah.
if we're slowly increasing the speed at
that acceleration.
so we don't feel a difference as it's. So how long would that take?
Huh? How long would it take? Well, then it's just simple kinematics. Distance is, let's just say the initial is 0. So then you just have half AT squared, right? 4.40 light years. 1 light year is 9.5 times 10 to the 12th kilometer. And then 1 kilometer is 1,000 meters. That's equal to half times the acceleration. Oh, the acceleration, 32 feet per second squared. So let's just say 9.8 meters per second squared.
Yeah.
That's it. So this kilometer cancel kilometer, light year cancel light year. For 4.40 times 9.5 times 10 to the 12. So let's just say 10 to the 15 divided by 4.9 square root of that. You will get there in that many years.
Pretty close to 9 to the 10. What's the square root of that?
92 million.
Second.
This is seconds, right? 92,361,313.6 seconds. Divide that by 3,600 seconds is 1 hour. Divide that by, right? So convert this to, divide by 3,600 to convert to hours. Then divide by 24 to convert it to days, right? And then divide by 365 to convert to years. So you always divide by 3,600. Well,
2.95.
2.95 years. It's not bad.
We just don't have anything to continue accelerating at this speed. Without
2.93 years, you can get a new colony started.
Wait.
Because
It seems too good to be true,
Yeah.
right?
the speed is constantly accelerating.
It's accelerating. The speed is constantly accelerating for 3 years. Can we do that though? Maybe the technology won't allow the.
Faster than light.
What would be the what would be the final velocity? AT, right? Acceleration is 9.8,
Yeah.
and time is 92.
If it's 4.4 light years, we couldn't get there in 2.93 years.
Why?
Because we had to go faster than the speed of light, no?
Well, that's what we gotta check now. What would your final velocity be? Right.
Yeah.
So then take the number of seconds and multiply it by 9.8.
Make sure there's nothing in between us and that planet.
Let's see, 3, 6. The final velocity is 9.05 times 10 to the what?
8.
8 meters per second. What's the speed of light? 3 times 10 to the 8. Speed of light is 3 times 10 to the 8. So for the last portion of your trip, you're basically going faster than the speed of light, right?
Okay, so to get the truth.
Even if you're not going faster than the speed of light, even if this number was something close to that, but smaller than that, I still think we couldn't do it because our technology doesn't allow the spacecraft to handle that speed,
For
those speeds.
essentially for years on end, constantly increasing.
Imagine
every
constantly increasing the acceleration, constantly increasing it every second by a rate of the same as gravity. It'd be awesome if it worked, but our technology now cannot allow that.
And we'd also have to adjust to not hit planets and meteors without.
That part is not bad actually.
Really?
Most of space is vacuum.
Okay.
You'd be surprised, like you can drive right through with your car. You can drive right through the meteor, the asteroid belt. You wouldn't have hit a single asteroid
So it's just all movies.
because most of the space is still empty.
What about gravity?
Huh?
Oh, planets.
You just have to avoid getting near the gravity of a planet. Try to go, and even then, most of space is empty. So your biggest issue is being able to accelerate at that rate and keep increasing the speed. The battery life of this, what's powering it, right? And can it power it for 3 years? Now, will humans eventually be able to do this? Yes, right? This is going to be like Magellan's first trip around the world, right?
How exactly does that work, like in space? Like here on Earth, we push off to something to get movement, or just in the vacuum of space.
It would just have to be some kind of jet, something that powers that jet. It could be some kind of nuclear decay that's happening, like a nuclear reactor that's making energy and then propelling the jet out
the energy backwards.
backwards, so that you propel forward. Newton's
Okay.
third law. That's
Yeah,
Newton's.
that's true.
Newton's
I
third
never
law is
thought
the
that.
basis of all motion. That kind of motion. Throw something back, and it in turn will throw you forward.
That's true.
So if you could eventually do it, you could do it. You could simulate gravity. So an interesting problem like such as being in an elevator essentially is a little time machine. Being in an elevator is a time capsule because for a little bit you are creating gravity when the elevator is accelerating. You're creating an extra bit of gravity that is adding to your weight and making you feel heavier. You see?
This is what we talked about last time, where it's like the planes that drop, they drop at 32 feet per second. So you're essentially feeling the
Yeah, you're feeling a little bit of the
weightlessness.
that's why it scares everybody.
Yeah.
The turbulence.
Yeah.
So so for the second stage, what weight are you gonna feel? Well, when you're going constant speed, you're not accelerating. You would feel your regular weight, which is which would be what? Just the 192, right? £192. How about in the third stage? So now as you're going up and the elevator is slowing down at a rate of 8 feet per second squared, what's going to happen? So now there's a normal force pushing you up, and then your weight is down, and then the elevator is decelerating. This part is a little harder to understand than the first part because the elevator is moving up, but it's slowing down, right? So that means the acceleration is down, but the velocity is up, right? So what does it mean to say acceleration is down, which means anything that's in the elevator, it's the weight of that object is greater than the forces pushing up on the object, right? So that means mg has to be greater than n, right? So mg minus n is equal to ma. I'm always writing it in the direction that the a is positive, you see. So since I know that the a is down, I'm writing the weight down first. So this is the force that wins minus the force that loses. So now this would be your 192, and then this would be 6 times 8. So the normal force would be 192 minus 48. And that would be let's see, 144 pounds. And so now you feel lighter than your regular weight. That one is a bit harder to understand. How is it that you feel lighter? So try to explain this to someone without using the N and the MG and the MA. Just try to say, okay, when you get in an elevator, the elevator is accelerating up, you're going to feel heavier than your weight. Why? Then when it's slowing down, you're going to feel lighter than your weight. So try to explain this concept without the MG and the MA. That's the best thing if you can do that. How would you say it?
There's a force.
Because when it's going up, like the floor is being pushed into you, you would feel that force going up into you.
As you're accelerating up.
Yeah, when you're accelerating up, and then when it's accelerating down, it's like you were initially like with a certain velocity, and the elevator slowing down, so you're kind of moving faster than the elevator itself.
I like his explanation because it doesn't use any math. I love that. Yeah, so he's saying when you're going up and you're slowing down, it's almost as if you're like trying to escape the ground. You're going at a faster speed, but the elevator below you is slowing down. So it's almost like there's almost like a separation being created. Yeah, I like that. See, no math in there. So therefore, the elevator is not pushing you up with as much force because the elevator is seeing you as if you're passing it. You know, you're almost kind of like lifting off in a sense.
So the normal force by definition is like the floor acting against you, right? So since the floor is moving, doesn't that change the value of the normal force? It's why that apparent weight's different.
So
Because it's pushing against you differently.
as a matter of fact, the normal force is the macroscopic concept that we give to you, the interaction that you have on the ground that you're sitting on. So how is the normal force created? Well, when I'm on the ground, gravity is pushing me down, and the reason that I don't fall into the ground is because the molecules of the ground have a certain elasticity, right? So imagine this is the ground, these are some molecules, almost as if visualize them with a spring, you know? These are the molecules that you have. So now, when you are going up at constant speed or even not going up at all, what happens is the gravity pushes you down, and in a sense the ground does go down a little bit, very, very microscopically, do you see? So the ground goes down and then pushes on these springs, which is the molecular interaction between the molecules. So it pushes down on the springs, and there's a certain point which the springs say, okay, I'm not going to let you go down anymore. So as you go down, the springs push up, and when 192, and then the gravity is 192 until the two are equal, right? But now, as to what Andrew was saying, when you're going up, but the elevator is slowing down, but you're still going at a faster speed, right? So then what's going to happen, you're not going to push down on the surface anymore as strong. So the normal force it's pushing down on you is going to be 144. You see? So if you're going, but the elevator is slowing, the amount by which you go down is not going to be as much. You see? So there is literally, on a microscopic level, a little separation that's created between you and the ground. Yeah. that without the electromagnetic force between molecules that holds them together, we would literally go through the floor. Because if you think about it, most of the ground is vacuum. Just like I was saying, most of space is vacuum. Because what's the atoms made up of? A nucleus and electrons that go around the nucleus, right? You know the spacing between the nucleus and the electrons? It's like 10,000 times the distance, the size of the nucleus. It's like, imagine this is the nucleus, and the nearest electron is like the edge of East LA College. There's that much vacuum, right? So literally, if I'm standing here, I should be able to fall through the ground. Just purely on space reasoning. My body, the molecules of my body should disintegrate and be able to go through that empty space, right? The only reason that's not doing that is all the electromagnetic forces that are holding that molecule to the other molecule, to the other molecule, to the other, to the other, and then your molecules are not able to go through that because they exert a force, a collective force that prevents you from falling through. Now in the future, what we'll be able to do is make a hologram of ourselves, you know, and then we'll start to penetrate through that wall. You know, if we can kind of take ourselves and break it up into a bunch of pieces, and then penetrate through that empty space, because most of the space of the wall is empty, then we can go up to the other side and then reform that hologram back to ourselves. So we'll be able to do that. I'm pretty sure. That's another technology that's going to be accomplished. Very futuristic, right?
What would be like the applications of that? Like drilling?
I would love that. Are you kidding me? I can think of thousands of applications. I want to walk through there right now and there's someone on the other side. Money? Stealing money from banks? Don't videotape that. Just between me and you guys, that you could cut that part out.
I heard people saying that they wouldn't want to go out and transport because they think that the person who come out of it wouldn't be them if they die.
Oh yeah, if they did that?
Yeah. I wouldn't go to them personally.
What are we anyway? We're just a bunch of we're constantly Googling everything. We're part of the internet anyway now, right?
There's like a whole movie on that, The Prestige.
Oh yeah, which one is that? I love all these kinds of sci-fi movies. Looper, I love.
Have you seen Fringe, the show? Where they talked about exactly what you just did about going through walls and robbing a bank.
Oh yeah?
Yeah.
And robbing a bank, literally that.
That's
Yeah, just robbing a bank, that's it. Well, yeah. The other one, which is the other one that I like, I always say. The Surrogate. Bruce Willis, right?
That was a good one.
Your surrogate living for you, right?
So you say.
Yeah, all these things, these are cool. But you know what? A lot of these sci-fi movies are the future of the tomorrow. You know, they're already happening. It's just we don't see it, but it's happening and will continue to happen. Okay, so that's a good answer. So 144, 240, and 280. Now, what if we make this acceleration 32? But we're still on Earth. So I'm not doing the example of you're in outer space and it's accelerating at 32. But you're on Earth and it's accelerating at 32. Can that happen? So would you want the elevator to accelerate up at 32 and then when it decelerates, decelerate at 32? What would happen?
No.
Okay, so now let's put 32 here.
You have twice 2G in the beginning. You have 0G.
Then it'll be 192, 192. So you literally would feel twice your weight. 384. So we would call that experiencing 2 G's of force. Can people experience that? Yeah, that's okay. Astronauts can experience up to 10, 11 G's. You know, so if the elevator accelerates up at 32, it's doable, but it's not very comfortable for the natural person. They're gonna go, whoa, you know. But now, how about if it decelerates at 32? So now we put here 32,
0 G.
0. So then what's going to happen?
Your weight is essentially.
So if you're slowing down at 32 and he's already going, this guy begins to float. That's the similar idea to why astronauts float in outer space, right? It's not that you're weightless. You still have a weight of 192. It's weird, right? He still weighs 192 pounds, but he's floating. Because the elevator that he's in, the compartment that he's in, is also decelerating. In other words, you're like this floating, there's a gravity of u mg, and then the elevator is also decelerating at a rate of g. Also, in a sense, you're both decelerating at a g. So with respect to the elevator, you're just floating. You know? So if the building was long enough, you could kind of simulate, you could train yourself for get the elevator moving really fast, and then slow down at the rate of g, and then continue slowing down for a long time. And you could train people to be astronauts that way, and just floating.
So if the space station, if instead of letting it fall at a constant speed,
The only difference with the space station is that the space station's acceleration is around the Earth, let's say, right? So imagine this is it. It's a centripetal acceleration equal to 9.8.
Right.
Or let's say equal to some other. It doesn't have to necessarily be 9.8. Let's say 3.5. But you're in it. You're also accelerating at a rate of 3.5 meters per second squared. Why? Because the gravity there is less, right? The gravity there is less. It's not 0, but it's less. G is equal to gm over the distance squared. Gravity of the universal constant of gravity times the mass times this distance squared. Right? So whatever the gravitational field there is in orbit, if the acceleration of the spacecraft is the same, then you and it are accelerating at the same rate, which is the same thing as saying you are floating in the elevator.
So just so things don't fail, they don't try to accelerate up constantly and just make fake gravity like you were saying earlier, right? Relative.
Well, you could make fake gravity by having this as a spacecraft that not only goes around the Earth, but you could also goes around its own.
Oh, okay.
Then you can actually have people walking on their spacecraft.
But I mean, like, can we
So
also
have it go like this and have it spin
but can we also accelerate away from the Earth constantly?
away from the Earth.
The whole ship,
Yeah.
and then it would,
Oh, you mean like this away
Yeah.
from the Earth and then circulate?
Yeah.
Yeah, you could do that too.
and then we could just like readjust.
You
every
could
few
go all the
months.
way to Mars, take a group of people to Mars, and then have it rotate
Yeah.
like this, and then you basically walk on the edge of the thing,
Yeah,
like this,
that's cool.
as in like this, right? And then as long as that acceleration is 9.8, right? 2001? Yeah, exactly. Okay, now let's do some other kinds of problems. So in this scenario, you're pulling a block 40 degrees. The block is sitting on a flat surface. There is no friction here. So what is the acceleration of the block and the normal force on the block? And the second question is, what is the minimum force needed to lift the the block off the surface. And what is the acceleration and the normal force at that point? C So what is the acceleration of the block and the normal force on the block? What is F min to lift the block off the surface? If F is F min plus phi, what is A and N of the block? So in the first scenario, we're just pulling with 15 newtons. So we got to do the free body diagram of this. The normal force of the surface pushes the block up, right? And then the weight of the block is down. Since the mass is given to you now in kilograms, so we convert to newtons, is going to be 6 times 9.8. So that's going to be 58.8 newtons is the weight. Right? And then we have here, so now we're going to break this force into components. 15 cosine of 40, 15 sine of 40. Okay, so we're going to argue that in the vertical direction, we'll call that the y. This is xy, right? So in the vertical direction, there's no acceleration. So we got n plus 15 sine 40 is equal to what? Well, if there's no acceleration, then this plus this needs to equal to the force that's down, which is 58.8. Right? So because you're pulling up on the block as you're dragging it, that reduces the apparent weight of the object. The normal force goes down, right? So this is called giving the object a certain amount of lift when you do that, right? So imagine I'm pulling the folder like this, see at an angle. So what's happening as I'm doing that? Even though I'm dragging the folder along the surface, but part of my force is pointing up. So what is that going to tend to do? That's going to make it's almost like the elevator case where this is kind of being lifting off the surface, right? So the normal force is going to go down. So N is going to equal 58.8 minus 15 sine 40. Okay? So this is where we're really starting what is considered the typical physics problems, right? The block, the inclined planes. So far we've been on easy stuff. It's not that easy, but you know what I mean. This is where it gets hard. Make sure you are on a degree mode here. So this is going to be 49.158. Okay, how about in the horizontal direction? Well, in the horizontal direction, since we didn't introduce friction yet, so the only thing we have is the 15 cosine 40, right? So then we have here, this is the y direction. And then in the x direction, we got 15 cos 40 is equal to 6a. It's mass times its acceleration. Notice here I didn't use 6a because the a was 0. I could have done it this way. Minus 58.8 is 6 times 0. It's actually even better if you write it that way because you can see it better. Right? Because the acceleration in the y direction is 0. So you just put 0 here. And then 58.8 goes over there. Right? So then you're going to have here a is going to equal
1.91.
1.91. So that's the answer to the first part. B, what is the minimum force to lift the block off the surface? And at that point, when it's lifting off, what is its acceleration and what is the normal force? Okay? Anyone know? So what does it mean to lift off? Well, it means to exert enough force to where this is what?
Equal to.
You see, it lifts off the surface. So, what should happen? The more force I exert,
It's on.
this component of the force needs to equal this. You see, when the vertical component of your force equals this, what happens to the end? The bigger force you exert, the normal force goes down until the end disappears. When this guy equals this guy, the object lifts off the surface, right? That's how you pick things up, right? Pick things up from the calculator or whatever it is, scissors, right? So when the amount of force you exert in the vertical direction is equal to the weight of the object, right? So that means the normal force is 0. See? Okay, therefore what's going to happen? F sine of 40 is going to equal to the weight of the object, right? Because this component of the force is going to be F. F sine of 40 is going to equal to 58.8. And you divide that, you get 'So that's a lot of force, right? Originally you were only pulling with 15 newtons. You're going to have to pull really hard, 91 newtons, in order to lift this up. Well, it's a 6 kilogram block. That's so heavy. That's a 6 kilogram. You have to lift in a very, very lot of force. Okay, so then what's the acceleration at that point? Just before liftoff. Right? So then that depends on the horizontal component of your force now, right? So F cosine of 40 equals MA. Right, so now you're going to put here 91.477.
$11.67.
That's very, very fast acceleration. But that's only in the x direction, right? AX. The y direction acceleration is still 0. So at that point, the object almost begins to lift off the surface and kind of glide along, but it's accelerating very fast along the surface. Okay, see if that all makes sense. Review what I've done so far. Take a minute. So you'll be able to follow it.
missed that. Why is there a 4 above the 9.8?
4 above the 9.8. I was just doing multiplication in my head.
Oh, okay. So
6
I'll make sure I
times
didn't write it down.
6
wrong.
times 8 is 48. Carry the 4. 6 times 9 is 54. Add the 4.
Oh, okay. Yeah, so I didn't
What
know.
you learn in
if
like 4th grade, 5th grade.
So I didn't know if I missed something. I was like,
Yeah.
Where's that 4? Give us a chance to try to take knowledge.
Yesterday, I don't know. Yeah, but I believe like I can't remember from it. It's just like it became out of nowhere. It's like nah, like I was aware that this was kind of Everyone does like because it keeps on. Yeah. Because you know sometimes that don't get related parts. Yeah. This is gonna be one of the hardest things to learn. I didn't have time for that. So you already
Okay. So far, so good. Okay, now we're gonna do the last part. If you exert 5 newtons more force, then not only will it just barely lift off, now it's gonna start to accelerate upward also, right? So if you exert 5 newtons more force, you're basically exerting 96.477, right? The force is going to be 96.477. So now what's going to happen? It's going to accelerate in the horizontal direction, right? In the x direction, we got what? We got the 96.477 cosine of 40 is 6ax. Now I'm going to write ax because it's going to have 2 accelerations. So I have to be specific that this is the acceleration in the x direction, right? Huh? X direction. X direction. Oh, so 96.477 cosine of 40 divided by 6. 12.318 meters per second squared. Okay, in the y direction is going to be 96.477, right? sine of 40. So that's the vertical component that you're exerting, the vertical force, minus the weight of the object, which is still dragging it down. So that's going to be 58.8. Is equal to 6ay. Now that's the acceleration in the y direction, right? So AX is a lot larger because you don't have to compete against gravity in the X direction. But in the Y direction, you're subtracting the force of gravity, and then you're exerting the force that you're exerting in the Y direction. Then you're equating them, you're subtracting them, dividing by 6. So the total acceleration is going to be 12.318 I hat plus 0.536 J hat. Meters per second squared. So this kind of resembles what happens to an airplane too. As the airplane builds up speed, the buoyant force on the wings of the airplane causes it to lift up, and it accelerates in the X direction, and then once it lifts off, it starts to accelerate in the Y direction, and it starts going up in the air. Okay, now let's do this problem similar.
You forgot to calculate the normal force.
Of what?
I think you asked for the normal force.
Oh yeah, the normal force for part C? Okay, what is the normal force? 0, right? Because once it's in the air, there is no normal force. So once it lifts off, and it's hovering on the surface, the normal force is 0. And then if it's in the air, the normal force is 0 too. Okay, so now now let's ask all 3 questions, the same 3 questions. Well, if the force is 15 newtons and you're dragging a block up an incline, 25-degree incline, so if the force is 15 newtons, what is the acceleration? What's the apparent weight? So the first, they're going to be all 3 same questions. And then B is going to be how much force do you need for the block to lift off the surface? And then C is going to be the same question too. Everything same 3 questions. Okay, so what's the free body diagram? For blocks that are accelerating along the incline, right? This is accelerating along the incline. We rotate the XY axis. In linear algebra, what is this called? The change of basis, right?
Yeah.
You rotate the axis so that the problem becomes easier for you.
Mm-hmm.
Because that's the direction, the X direction is the direction of the acceleration. See? So then the normal force becomes this way. And then the weight becomes like this, 58.8. So that means every time I break my forces down, I'm going to break the forces with respect to this rotated XY axis. So my rotated XY axis is like this. This is my X axis. Imagine this force as if it's originating from the center. Okay? So this is 40 degrees. Right? So this is going to be my X axis, my rotated X axis. This is going to be my Y axis. Right? So now I'm going to break my forces. This one here is going to be F cosine 40. This one here is going to be F sine 40. Okay? And then I'm gonna have to break the weight into components. But the normal force, I don't have to break into components because the normal force is exactly in the y direction, right? So this angle is gonna be 25, right? Same as the angle of the incline. So that's the angle that the weight makes with respect to the y-axis. Now, why is that angle and this angle the same? Well, because if you think of this line, the horizontal line, this is 25, right? If this is 25, this is 25. Well, if that's 25, that means this one is 90, so that means this is 55. Is that right? No, 65. And then this is 90, therefore this is also 25. See? So this component of the weight of gravity, and then you got this component of the weight of gravity. So you got the component of the weight of gravity that is in the y direction, right? So then what's that gonna be? 58.8 cos 25, because it's in the adjacent to the 25, right? Then you got the component of gravity down the incline, 58.8 sine of 25, because it's opposite to that angle. So this is kind of a weird case where the y component is cosine and the x component is sine. That's okay because the angle that's measured is measured from the y-axis, right? So you shouldn't be surprised, well, why is y component cosine? Well, that's because 25 ended up here. This 25 and this 25 are the same. Okay, so how do you answer the question A? The question was, what's the acceleration and what is the normal force, right? So to solve for the normal force, you say n plus f sine 40, which in this case was 15 sine 40, right, is equal to what? 58.8 cosine 25. And then you can solve for the normal force. Okay? N plus 15 sine 40 is 58.8 cosine 25. Okay, now, how about the acceleration? Then you got the acceleration is 15 cosine 40, which is this way, right? Along the x direction. But now this one is opposing that. Minus 58.8 sine 25 is equal to 6ax. I'm getting negative. Notice how different this was than the answers that we got for part A of the flat surface. For the flat surface, what did we do? Well, for flat surface, we didn't have to worry about 58.8 cosine 25. It was just 58.8, right? Flat surface. It was n plus 15 sine 40 is 58.8. So it's always good when you do a new problem, then compare to the old problem and see what changed. You know, especially if they're similar. With the flat surface, we didn't have to worry about cosine. Why? Because the flat surface is kind of like being on an incline that is 0 degrees, right? If you think about it. So it's like cosine 0, and cosine 0 is 1, right? So in that case, what happens? The normal force came out larger or smaller? It should come out, this case should come out larger, right? Because this is, cosine 25 is reducing the number. What did it come out the normal force in the flat surface? 49 newtons. So from there, what do we learn? What generalization can we make? When you put a block on the surface, it feels less weight. It feels less heavier, right? Does that make sense? So in other words, if I put a scale below it here, the scale reading is going to be less, right? See it?
Is that why when you like kind of rock back and forth on a scale, it changes your weight?
Yeah. It kind of, yeah.
Because I mean, you're kind of leaning. So
And the scale is leaning with you?
No, like if you like stand on a scale and you kind of lean back. Or
That's
forward.
probably a little different because here the scale would have to actually lean with you
Oh,
and
okay.
support you.
That's true.
That's probably a little bit different effect. Here the scale I would put here, and then you and the scale would be on an incline. You know, and then the scale would read less. Right? Why? Why is it reading less?
Because normal force isn't just straight down.
Because they used to base the full force of gravity, but now it's at like a slant.
Okay.
Like the actual
Maybe the actual vertical component would be higher since it's pulled at an angle that was already at an angle compared to an angle that was on that surface. So instead of the force of inner pattern was on that surface, vertically using the x and y axis like shifting, but with respect to the actual angle, you would like
Yeah. I mean, your answer was good, but I kind of wanted, again, a very simple answer that you can just take your 9-year-old brother hiking and with a scale in your hand, weigh yourself, and then start going on a hike. And then as the hike goes up the mountain, put the scale there, weigh, and then your brother weighs himself. And then you say, you see the scale is showing less. And then your brother asks why. Try to make it as simple as possible.
You're not getting pushed directly into the scale. You're getting pushed partly into the scale, but partly away from it as well.
Yeah. Imagine like you're like this.
Yeah. We're not being pushed into it. We're being pushed like the extra component, like you were saying, is getting pulled.
So would you use the word component to your little brother? Or you would try to avoid that word? Do they understand component?
I don't have a brother, but I would teach him young if I could.
Yeah. Component might be hard to understand, but maybe you say, but the first way you said it like, the gravity's pulling you down, but the road is inclined.
Pull away, or pull this way.
And maybe the ultimate thing you can do to him is to say, hey brother, what if we were on a road that was like this, like mountain climbing, and I were to stand against the scale? What would the scale read? And maybe that might get him to say 0, because it's no longer supporting you. And both you and it would fall. Right? Because the ultimate end of this is when you're on a 90-degree incline, there's no normal force. Unless you're pushing your legs against the ground, you know. You yourself are pushing your legs. But if you're just relying on gravity to do the job, the gravity is just going to drag you down and drag the scale down. You see? So as you're walking up the incline, gravity is beginning to more drag you down, and the road is supporting you, but only a portion of your weight. It's only supporting a portion of your weight. So don't use the word component. Just say portion. Just say, little son, little brother, the road only has to support a portion of your weight. And that portion is this vertical portion, the portion of the weight that's the portion of your weight that's into the ground, right? So by the time you go over here, all your weight is down. None of it is into the ground. You see? And therefore the normal force is 0. You see? Okay, then for this part, we were completely missing this portion. That's even a bigger difference than this. For the flat surface, we just had 15 cos 40 is equal to 6ax. You see? So we were completely missing this portion, which is the what? What is this? Yeah. It's the portion of the weight of gravity opposite in direction to the direction that you're trying to move. Right? And it's opposing you. When you're on a flat surface, gravity is not opposing your motion. It's just completely counterbalanced by the support force. But when you're trying to walk uphill, why is it harder to walk uphill? Because part of your weight is now down the road. Let's see.
I feel like we could use that for a lot of things. Like,
Oh yeah.
is that when you is that the point at which you would slide that force would pull you back down?
Which one? 58.8 sine?
Yeah, once that's bigger than.
Yeah, well in that case, look what happened. In the flat surface case, we definitely got an acceleration of positive. Here we're getting negative. Why? Because that's telling us that even if you pull at 15, that's not, this component of the force is smaller than this. So this picture is not good. 15 is actually very small. You see? So that portion of it is much smaller than this guy. So that's why the block is accelerating up. It's almost like I'm trying to pull on a car, let's say, a very heavy car up the hill, and I'm not exerting enough force, and the car is actually going down the hill.
So like questions were like, how much force do you need to be able to move this upward? We need to just know that that's where we're going to.
Yeah, exactly.
That's what we need to
Like we can add more questions to this. Like question B was, how much force do you need to lift off the surface, right? But before we even get to that, I might be able to insert a new question and say, how much force should you push with so that the block goes up at constant speed? See, that we didn't have that question in the flat surface problem, because in the flat surface you can't go at constant speed. As soon as you exert the force, it's accelerating. Why? Because I'm ignoring friction. This is Monday, I'm ignoring friction. Wednesday, friction will come, and it will completely complicate everything, right? But if you're on a flat surface and you're pushing with a force and it has no friction, you cannot create a constant speed situation. As soon as you exert the force, the thing accelerates.
Yeah.
But now I can say, what F do you need to go at constant speed? So that you can drag the car up the hill at constant speed. Well, then what would we do? We would make this F larger and larger, right? Until this component of it exactly equals this. You see? So then we would say what? F cos 40 is equal to what? 58.8 sine 25. $32.439. Now we go to question C, and now we can go back and ask, how much force do you need for the block to lift off? How much F to lift off? Then what would we do? Well, now we would keep continuing to make this larger until what? Now the criteria is that we want to make it large so that this disappears, right? And disappears. So now what's the vertical component of the weight? See, it's very visual. If you don't draw this picture and you don't draw these vectors, you're not really understanding how to set up that criteria, because the algebra portion is easy to do. Then you're gonna say, okay, this component of the force has to equal this guy now, not this guy. The vertical component has to equal this guy so that the n is 0.
So 15 sine.
So
40.
F sine of 40 equals 58.8 cosine 25. $82.906. This is F liftoff, we can call it F liftoff. 82.906. Now, which one was easier to lift off? The block on the flat or this one? I think that one was 91 newtons, right? Yeah, it's about 9 newtons easier to lift this off. Right? Because my force only has to contend with this component of the weight. Right? This portion of the weight. As long as this is this, then n is 0. So that's why it's easier to lift off on an incline. Which seems like it's kind of counterintuitive, because you would think it's harder to lift off because your gravity is fighting against you. That one you're confusing two issues. The acceleration we get when it lifts off is going to be less than the acceleration of the flat road. Because why? Because this weight of the thing is fighting against you. Right? The resultant acceleration is going to be less than the flat, but the point at which lifts off is easier.
It's like confusing because we're also having to support our own weight while we're pulling it so intuitively.
Yeah, you think it's harder to lift off.
Our weight's being pulled.
Right? So in other words, if I incline this, right? If I incline this like this, it should be easier to lift this up. Right? Versus if I go like this, it should be harder. Now, it's not too noticeable with the folder because it's a light object. Right? But if it was a heavy object, it might be more noticeable. It should be easier to lift off if it's on an incline. Okay. Yes.
If you picked it up, and you were on a flat surface, would that make a difference?
Oh, it's instead of
Straight up.
I think I'm where I am probably. You mean if the person is actually standing here versus here, and then.
Oh.
Right now, I am not doing that much detail. I think.
It would be the direction in which it's going, right?
You want to make it a hard problem.
Like it's the same
I think
force,
I'm
but
considering.
the angle would be different.
I'm considering where the person is located kind of irrelevant. Maybe he's outside of here. I think for our purposes, it's okay. Even if he was here, let's just treat it the same. Where he is, in reality, there might be slight differences. Because when you're on an incline, you're also having to contend with your own weight and stuff. So there might be some slight differences, but let's ignore that for now. Okay, so now what's the corresponding acceleration of the block when it lifts off? So then how do we do that? Then we take the horizontal component of the force minus the weight. No, not 58.8. I meant 82.096 cosine of 40 minus what? So that's this component of the weight minus this guy, 58.8 sine 25. Is equal to the mass, right? Which is going to be 6ax. So the acceleration that it has at liftoff is going to be smaller because this guy's fighting against you, right? I think that one was bigger, right? That was 11 something meters per second squared. So this one is accelerating along 6.44. The AX means it's accelerating along the incline at 6.44, right? Because remember, our X direction is along the incline. Okay? Okay, how about the last question, the one where you exert the force 5 newtons greater than that? So then what's going to happen? We'll call this question D. F equals F min plus 5. So that's going to be what? 87.096. Well, once you exert the force greater than the force needed for liftoff, what's going to happen? Now no longer it's part of the incline, and I think I should now change my bases back to x regular xy. It's no longer accelerating along the incline. So forget the incline now. It's as if it doesn't exist. So imagine a block where you're exerting a force how much? 87.096. And what's the angle that you're exerting the force from the horizontal? Because once it lifts off, incline is gone. So then the total angle is 65, right? 40 plus the 25. I'm changing my basis so that my x is this way and my y is this way, right? So now it's going to be 65 degrees. So now my acceleration in the x direction will be this guy, the horizontal, and my y is going to be this one. No longer along the incline. X, right? So then what are we going to do? The weight is this way, 58.8. So 87.096 cosine of 65 is equal to 6ax. That one is probably better, this one, instead of calling it ax, even say acceleration up the incline. Right? Because that's really what's happening. It's accelerating along the incline. But now it's in the air. Right? So now 87.096. Okay? So what does that come out? Six point 192 meters per second squared, and then the acceleration in the y direction is going to be what? 87.096 sine of 65 minus 58.8 is equal to MAY. Huh?
3.478.
Nice. Nice problem. The incline plane was definitely harder. You have to worry about the way that the component of the weight. Call this A1. Right, so if I let go of this system, what will be the acceleration of the 5, right? Because what's going to happen, if I just let go of it, this guy's going to accelerate down, this guy's going to accelerate up. What should the 20 kilogram do? Assume all surfaces are frictionless. No friction here, no friction here, and then no friction here.
The 20 the big one.
Huh? I think the 4 kilograms should accelerate down. The 5 kilograms should accelerate this way with the same acceleration, right?
Yeah.
And then the 20 kilograms should go to the left. Why is it going to go to the left?
The point at
The incline, the pulley.
the pulley.
There's some force there,
Yeah,
right?
Force, no natural force is like
Oh yeah. The pulley is exerting a force on the strings this way,
yeah.
and then the strings are pushing on the pulley. Yeah, that's one explanation. Yeah, that's great. So that makes the 20 kilogram go backwards. Or you can argue by conservation of center of mass. If the center of mass of the system is, let's say, here, and there's no friction forces, as this guy moves to the right and down, this guy should move this way to conserve the center of mass should be staying in place, right? Either that or the forces explanation. That's good, the force. So how do we find that? So the force here is what? 4 times 9.8, 39.2 newtons. Then there's a tension in the string, right? And then there's tension here. Is that it? Those are the forces on the system, on the top system, right?
Yeah.
But hold on, maybe there's a, let's see here. Maybe there's a force from here to here, interaction force.
We don't know. Is it like I don't know.
A mutual force here. You might say, well, what if the block was small? What if it was in the air?
Yeah,
What's going to happen?
so
Is the block going to tend to swing and touch it, or is the block going to go like that? Which way is it going to swing?
So the bottom, the big block is still moving to the left, so should swing to the left
This one? Swing to the left?
because the whole bottom system is
This is going to the left.
Assume it's
so
out
the
by reference.
It's going to swing out? You're saying this one.
I would think it would swing out just because, I mean, not only that, but it's moving, so the fact that even if
Yeah.
it was still going straight down, if this one's moving, it's going to seem like it's swaying out, isn't it?
Yeah, if this one is going this
That-
way,
Even if that fell straight down, it would still swing out, wouldn't it? But then that would pull it back. Huh. What's that going on in this problem?
okay, I believe this is what's going to happen here. This is going to be F, F. You're right. So this one is going to swing this way slightly. This one is going to accelerate back, right?
Mm-hmm.
This is going to be A2, right? So now the A1 is the acceleration of this guy in the block's reference frame, right? As it's accelerating down. So we have here 39.2 minus t is equal to what? 4a1. It's accelerating down, right? And then the top one, t is equal to 5a1, right? So that's your regular problem. Basically, that's the kind of problem that you would solve in the introductory physics courses. You know, imagine this block, instead of being a block, is like a table attached to the ground. And I just asked, what's the acceleration of this guy and the acceleration of this guy? Then that's basically the regular problem. Then you do two equations, two unknowns. Then you take this, you substitute it here. than you saw for A1. Okay? So acceleration A1 is going to be 4.355. So this gun is going to accelerate down at 4.355. This one is going to accelerate to the right, 4.355, right? Now on top of that, there's going to be this guy's pushing down on this guy, and this one is pushing up on that one, right? So on this system, on this two block system, there is a force like this, pushing up on it, right? The vertical component of that force is canceled out by the normal force here, right? But the horizontal component of the force, right, makes this system accelerate forward, because conservation of mass, a conservation of center of mass, right? This guy is going to accelerate this way. This one is also going to accelerate this way. This one is going to accelerate back, right? So that the system is center of mass is conserved. So then we're going to have here this data, but then we don't even need to know what that data is. You're going to see that it's cancels. You just have F cosine theta is equal to the total mass of the system is 9A2. Right? That's the force that this system exerts on this two. Right? And then this system here, in return, exerts a force back on this guy, right? So then we're going to say F cosine theta is 20A2. No, hold on. The acceleration is okay. You know what? Let me think about this more detail. The first one is going to be a little bit challenging, but I think the second question is going to be a little bit easier. So we'll continue this problem Wednesday. I'm going to redo this and come out with the more details of what's happening here in the interaction, because we're also running out of time. Okay, great lecture. You can see chapter 5 is more demanding. So for this one,